Hello, everybody. We've been talking about the Laplace transform, and we've been using it to solve differential equations. Well, one of the things that can come up when you're solving differential equations is a situation where the force that's being applied may not be continuous. You could imagine if you suddenly turn on a motor and then it starts to supply a force, just all of a sudden. Well, that's not going to be a continuous, smooth progression of force. That's a force all of a sudden. Or if we all of a sudden, run into something, or something collides with something else, and now it's all of a sudden supplying a force. These are sudden forces. So these may cause discontinuous forcing functions, or forcing functions that at least can't be expressed as a single function. They need to be expressed as two separate functions. So how are we going to deal with this? Well, we're going to deal with this by using something called a step function. And so that's what we're going to be talking about, and we're going to be looking at how to compute the Laplace transform of the step function in this video. All right, so the step function, the unit step function, also known as the Heaviside function, is expressed like this. It's a function that's equal to 0 when t is negative, and it's a function and it's equal to 1 when t is positive. What does the graph look like? Well, there it is, right? And you can see it's just a step. It's 0, then all of a sudden it jumps up and becomes 1. So it's a very simple function. It's just one of two constants, 0 or 1. But it has this step. Now, I called this the Heaviside function as well. Why is that? Well, it's named after Oliver Heaviside. Oliver Heaviside is a mathematician from the 19th century, and pretty amazing guy. He's self-taught, and he learned mathematics, physics, engineering, and he's credited for formalizing Maxwell's equations, which describe electromagnetism. He didn't come up with them, but he wrote them down in the way that we know them today. All right, well, back to the Heaviside function. One of the things we're going to be doing with this Heaviside function is we are going to be, manipulating it a little bit. And one of the things we're going to do is we're going to be translating it around. And so if you just take t minus a, if you plug that in place of t, what you're going to get is you're going to get the step function that's translated a units to the right. All right, so let's see how that works. So over here in the graphing software I'm going to turn off the step function and turn on the translated step function. Now here I'm translating it by a equals 0, so it's not translated at all. But if I start subtracting off numbers from t, you can see that the step translates around, right? So the larger a gets, the further I shift it to the right. If I make a negative, I get a shifted step function shifted to the left. Right, so we can shift this step function around by manipulating that parameter a. Another thing we can do is we can turn it upside down. If I take 1 minus the step function, well, then everything that's 1 will become 0, and everything that's 0 will become 1, and so we get this guy. So this is another function that we'll be using and obtainable from the step function. This is just 1 minus the step function. Okay, so what can we do with this step function? Well, like I said, we can use it to express functions that are expressible in pieces. So a lot of times you'll see a piecewise defined function, something like this, say. Suppose I have a function f of t, and it's equal to 3t minus 7 when t is less than 4, and it's equal to 2t when t is greater than 4. And so it's two different pieces. How do I express this function in terms of the step function? Well, if you think about what we need to do here, we need to have this function while we're less than 4. So what I'm going to do is I'm going to multiply this function by a function that's equal to 1 up until it gets to 4, but then all of a sudden becomes 0. Well, we can get that from the step function, right? If I just look at this picture here, I basically just need to move this blue graph over to here. It's equal to 1 up until we get to 4, and then it becomes 0. Now, how did I get this? This is 1 minus the step function translated 4 units to the right. Okay, so what is that again? That is 1 minus the step function translated 4 units to the right. That is the picture that we just saw. And I want to multiply that by this. So what this will give us is it'll give us a function that's equal to this piece up until we get to 4, and then all of a sudden it becomes 0. Now what I want to have happen is I want it to now become 2t once I get beyond 4. Well, that means I want a function that's equal to 0 up until 4, and then all of a sudden becomes 2t once we get past 4. So for that, what I'm going to use is I'm not going to use the upside down step function, I'm going to use this one. Right? So if I multiply this function by 2t, it'll be 0, and then all of a sudden I've got 1 times 2t, just 2t, once I'm beyond 4. So that's just the normal unit step function translated 4 units to the right. So to get that piece, I will just add u t minus 4, the translated step function, multiplied by the piece that I want. Now we can write this, we're essentially done here, but we can write this in a little bit neater way. We can collect the u t minus 4 pieces, the step function pieces, and put them together. All right, so let me distribute this guy in here. So I'm going to, when it comes over here, I have 3t minus 7, and then I have these ut minus 4 pieces here. I'm going to have a 2t minus a 3t minus 7 part. Okay, so I'm going to have 2t minus 3t minus 7 all multiplied by ut minus 4. And now I can do a little bit of simplification here, right? Looks like I'm getting 7 minus t in there. Okay, and so what we're able to do is we're able to write a function that we would ordinarily write piecewise using this notation. We can write it all in one line using step functions. Laplace transforms of step functions. So what we're going to be looking at here is the Laplace transform of a step function times another function. Now, I've written my function as a translation of a function, t minus a I've inserted in there. And you know, whatever function you have, you can always view it as the translation of some other function. So this is completely general for us. This will allow us to treat any case. Now, how do we compute this Laplace transform? Well, we'll just use the definition, right? So it's the integral from 0 to infinity of e to the minus st times this stuff. Okay, there we go. Now realize that this function is equal to 0 up until I get to a, and then it becomes 1. So that means the integral is 0 up until I get to a, so I can just write this as the integral from a to infinity. And then when it's past a, this function is just equal to 1, so it's essentially just gone here. I just got this left over. So I really just have this business. Now what I'm going to do is make a change of variables. I'm going to let x equal t minus a, right? So that then dx is the same as dt, right? And let's just insert this. Now let's think about what happens to the bounds here. Well, if this is going from t equal a to infinity, well, when t is a, x is 0. So our new integral in terms of x will go from 0 to, well, as t goes to infinity, x will go to infinity. So it goes from 0 to infinity. Now t is equal to x plus a, so I can insert that in here, right? So what I'm going to get is e to the minus as times e to the minus xs f of x dx. Now, notice that this piece right here, e to the minus as, does not depend on x, so it can be pulled outside of the integral. And what we have left over here, the integral that's left over, you should recognize that that's just the Laplace transform of f. Our dummy variable, instead of a t, as it usually is now an x, but that doesn't matter. This is just the Laplace transform of our function f. So what we have here is e to the minus as times the Laplace transform of our function f. Okay. So this is the property that we wanted to establish, that when we multiply a function times a step function like this, we can express it as follows. So let's go back to the example we were looking at before. We had this function here written piecewise. We were able to express it in terms of a step function. Now what I'd like to do is compute the Laplace transform of this. Okay, so to do that, what we need to do is we need to express it in terms of pieces that we know how to compute the Laplace transform of. Well, we know these. We can look these up in the table, or we might just remember what these are. This piece will know what to do with it when I get this function also written in terms of t minus 4. Okay, so let's go ahead and express it out that way. This thing is w of t minus 4 times u of t minus 4, when w is what function? Well, that's the function that I would get if I plugged t plus 4 into this. Well, what's that? That is 3 minus t. Okay, so you see, we've had a function here, and now we wrote it as a new function of t minus 4. And you see that if I plug t minus 4 into this function here, I get exactly back to this. They are the same. Now, why did I do that? Well, because when I have it in this form, I know how to compute the Laplace transform. That's what we talked about a little bit ago. Right? So that's what we're going to do next. If I want to compute the Laplace transform of lowercase f, which I'll call capital F of s, I'm going to compute the Laplace transform of each of these pieces, because the Laplace transform is linear, so I can just do it piece by piece. What's the Laplace transform of 3t? Well, it's 3 times the Laplace transform of t. The Laplace transform of t is 1 over s squared. So this becomes 3 over s squared. The Laplace transform of 1 is 1 over s, so the Laplace transform of 7 is 7 over s. Now, how do I do this piece? Well, remember the result that we just showed. We said that this is going to be e to the minus 4s times the Laplace transform of this function. What's our function over here? Well, it's 3 minus t. The Laplace transform of 3 is 3 over s, and the Laplace transform of t is 1 over s squared. And so here we have it. We have completed our Laplace transform of a piecewise defined function. And what this will enable us to do is to solve differential equations now, where on the right-hand side we have a piecewise defined function. If that was our forcing function, if this was our external force, if we had a differential equation of this form, let's go ahead and put coefficients out here. we had a forcing function over here that was piecewise, we now know how to handle this because we will just take the Laplace transform of both sides, and now we know how to compute the Laplace transform of the right-hand side. And everything else proceeds as we were talking about before. So I think that does it. I think that tells us exactly how to deal with that. I didn't go through an example of working out the differential equation. I'll let you do that on your own, but you'll see it works out just as we were doing in the previous, as you saw in our previous work and previous videos. So that's it for today. See you next time.